Welcome everyone to the Full Spectrum series. My name is Nick Valentino. I am an assistant director in the Hajim School of Engineering and Applied Sciences at the University of Rochester, and I'm going to be your host for this series. This is the fourth year of the Full Spectrum series, where we invite faculty to discuss and explain their fields in an effort to inform and educate prospective and current students, parents, and alums on the problems that engineers and computer scientists are trying to solve. So if you're watching this and you're interested in learning more about problem solving and about engineering, you're in the right place. Today, we're going to discuss aerospace engineering, a new minor at the Hajim School. Our guest is Dr. John Lambropoulos. Dr. Lambropoulos earned his PhD from Harvard University. He's a professor of mechanical engineering, a professor of materials science, and a distinguished scientist at the Laboratory for Laser Energetics. So, Dr. Lambropoulos, thank you for being here. You really have a great deal of responsibility on campus, so we're really grateful that you can help us learn more about aerospace engineering.
Great, thank you very much, Nick, and again, everyone who will be listening to this video recording, welcome. And by the way, if anybody wants to get in contact with me, please contact directly Nick Valentino. He can provide to you my email address. So recently, the University of Rochester this past year has put together a minor in aerospace engineering. And I'd like to share with you some exciting content about this minor, both about the content of the minor at U of R and also about aerospace engineering as a profession. And I will put this in context both within the Department of Mechanical Engineering, where I'm a member of, and also within the Hajim School of Engineering and Applied Sciences, which is our group of all the engineering departments, including computer science and data science, and of course, within the context of the University of Rochester. So let me share here my slides. Okay, here we go. So let me share here the slides. Okay, so the first point I want to make is that, and you will see the way I have organized the top third of this is we're part of the University of Rochester. I think the concept of a university is very important. We're not a technical institute. A lot of the students studying at the university have interests outside of STEM and engineering. And as I said, within the University of Rochester, we're in the Art, Science, and Engineering, the Hajim School of Engineering and Applied Sciences, and the Department of Mechanical Engineering. So as a quick introduction, I want to make the correlation between mechanical engineering and aerospace engineering. And I want to convince you that mechanical engineering and aerospace engineering have about a 3/4 overlap, and then about a 1/4 sort of diversified material that distinguishes mechanical engineering from aerospace engineering. So basically, what is mechanical engineering? In a nutshell, you analyze structures and why structures may or may not fail. I hope they don't fail, collapse, or catastrophically fail. What kind of materials are ideally suited for different types of applications? It could be fluids, it could be gases, it could be liquids, it could be solids, it could be plasmas, whatever the materials may be. Fluids, as I just mentioned, and just as importantly, how do you produce energy, and how do you convert energy into power? In other words, how can you deliver power to power different gadgets, let's say, such as cars, aircraft, bicycles, boats, and so on and so forth. And the basic work that mechanical engineers do is to assess a problem, to analyze this problem, and then design in order to solve a problem. And this notion of design is very different from between engineering and sciences such as physics or chemistry or biology, because engineering design is an important part of the engineering profession. And I'll talk about this here in just a minute. Now, what is aerospace engineering, which is the topic of our presentation with Nick today? So there are 4 basic pillars in aerospace engineering. And I think everyone will be able to identify the importance of these pillars. Number 1, aerodynamics. In other words, how do we create lift in order to, for example, an aircraft or a satellite or the International Space Station or the Space Shuttle, how do we take something that's heavier than air and make it lift? We need lift forces. For that, we use things that we call airfoils or wings. Now, something must move through space, so we need propulsion to create thrust. And of course, when we move through air, because air is a viscous gas, we need more thrust. if we move in outer space, we need significantly less thrust because there's nothing to retard, to hold back, to decelerate the motion of a satellite, for example. We need to have control mechanisms in order to be able to navigate, for example, an aircraft, because an aircraft flying through the air, you will see that as aircraft approach airports, you will see that there's always this sort of back and forth controlled motion, which is very important to make sure that the landing or the takeoff is done safely. And lastly, just as importantly, the materials we build aerospace structures with. So that's very important. And of course, with materials, there's a class of materials. I'll give you some examples in just a minute. We call aerospace materials. The primary driving force behind aerospace materials versus mechanical engineering materials, that for aerospace materials must be very light. It costs a lot of money and a lot of fuel and a lot of investment to put something that's heavy up on the air. Therefore, the materials must be light. So the lightness of the materials, while being strong and safe, is very important. And again, as I mentioned before, for mechanical engineering, what do aerospace engineers do? They assess a problem, analyze the problem by using science and technical tools, and then design structures. I'll give you some examples of these designs in just a minute. So at U of R, we have, as I mentioned, this year in 2024, a minor in aerospace engineering. It's very exciting. A lot of huge excitement among the undergraduate students and prospective students, which consists of 4 courses. Essentially, the 3 what we call core courses and 1 elective, give a little bit of freedom of choice to the students. And as it so happens, I'm teaching literally as we speak this first brand new course, ME 102, which is called Introduction to Aerospace Engineering. And this course, just to give an idea, has 3 labs, hands-on labs that the students actually execute. One is to understand what air is. And of course, air is something that we breathe, something we move through, but air is also a technical fluid, a technical gas. So understanding the properties of air for aerospace is absolutely critical. Secondly, an experiment using a wind tunnel, a 3D printed wind tunnel to understand how lift is created and how velocity is measured in aerospace applications. And thirdly, the notion of the third lab is on adiabatic compression, which is very technical, very esoteric. Very few people know what it is, but adiabatic compression is essentially a very fast compression of a gas, which results, for fundamental scientific reasons, to a very rapid increase in its temperature. Therefore, if you want to ignite a gas, which is at room temperature, first you compress it very rapidly. Its temperature rises very rapidly, almost instantaneously. Then you can ignite and create combustion. So this is. And also, we have submitted a proposal to the New York State Department of Education for a master's in aerospace engineering. The master's consists of 4 required core courses and 4 elective courses. There are thesis and non-thesis options. And I'd like to mention the master's because although mostly high school students and their parents may actually read this, I always tell students, always think when you go to university, 4 years of undergraduate education go by very quickly. So always have in the back of your mind plans for what you will do, possibly further your education after you graduate. Therefore, thinking about a master's degree, it could be in aerospace engineering, in mechanical, or so thinking about furthering one's education is never too late. So you may as well start early about this planning.
So, Professor, if we have students, because this is kind of nice because it's bookended. So we have students that are interested in aerospace, but also interested in mechanical engineering. They're now having the choice of that first class being the aerospace course, introductory course, or the engineering of bridges as 2 different options that you can do going.
Correct. Okay. Correct. So these are so this introductory course is what we call the Introduction to Engineering course, and there's 7 or 8 of such introductory engineering courses, 1 or 2 each in different departments. And any student can take any of those introduction to engineering. So introduction to aerospace is the aerospace course for actually doing that. Correct.
Right. Thanks.
So what do our graduates actually do? About 1/3 of them, 30 to 33%, go into graduate school, master's or PhD degrees. The rest go into industry or maybe the services. There's some very exciting opportunities for engineering graduates. They can go. A lot of them do eventually go to business school because business schools like to have students who can think quantitatively, break problems. Remember again, assess, analyze, design. So they assess, analyze. This quantitative view of the world is something that's very attractive to business schools, and perhaps less prominently, but very lucratively, law school, specifically for the area of patent law, which is a very lucrative occupation. And for that, you need a STEM degree, ideally an engineering degree. So that's a terrific. We've had quite a few students who have gone into law school, especially about engineering students. Certainly, engineering students at U of R like entrepreneurial things. They really like to do things that involve essentially taking a technical idea that hasn't been made into a product, get a small team of engineers, scientists, maybe business people to make this idea into a reality, get some capital vested, usually from one's parents initially, and then maybe from venture capitalists. Typical starting salaries for BS in MECI on the order of 80 or 90K, and then you can see the added sort of tag for people who have a master's degree in engineering. So this is important, and I mention this because sometimes I don't know if an 18-year-old, for example, is concerned about what salary they will be making or not making 4 or 5 years down the road, but parents are certainly interested to make sure that they're involved in something that's rewarding of their education, because education, of course, is significant involvement at the family level. I always like to bring two lists in this context. So this first list is put together by NAE, the National Academy of Engineering. It was put together in 2003, and it is called the greatest engineering achievements of the 20th century. So that's the past century, right? And you will see from here there's 20 highlighted areas. I've highlighted in green areas which are specific to aerospace, airplane, electronics for communications, spacecraft, high performance materials. I've highlighted in red areas which are specific to mechanical engineering. But the point I want to make is that when you look at this list, you will see that each one of these items can be identified with almost clear matching parallel with specific engineering disciplines: electrification, electrical engineering; airplane, aerospace engineering; radio and television, electrical engineering; air conditioning, refrigeration, mechanic. So you can see from here what I mean by this. The point I want to make is that the list was published in 2003. If you go back 100 years before, in 1903, which was the year that the Wright brothers first demonstrated heavier-than-air sustained flight. In 1903, none of these technologies could be even dreamt about. Therefore, in 100 years, we make huge progress as engineers. Now, the real challenge is that NAE has also published what's called the greatest engineering challenges for our century, for the 21st century. And you will see from here that now the list is more wordy. In other words, you see that each item has like 3 or 4 or 5 words describing each of these items. The point that I want to make in this list is that this list of challenges, these challenges are very multidisciplinary. So it's not clear how to identify, for example, engineering, number 7, engineering the tools of scientific discovery. Well, is this for biomedical engineering? Is it for optical, mechanical, aerospace? Or is scientific discovery something that's common, therefore equally challenging, and needs a multidisciplinary approach from everybody who will be involved? That's exactly the point. Therefore, if something is multidisciplinary, professionals in that area, including students, must communicate across disciplines. How do you communicate across disciplines? You need to be able to write, you need to be able to present orally, verbally your ideas, and you must be able to address these 14 human needs. You will see from here. Need number 1, look at the adjectives: economical. Item number 3, clean water, clean. 5, personalized learning. And then you see scientific discovery. So you see from here that to characterize those adjectives and these challenges, we need the multidisciplinary approach. And I believe very firmly that the university is exactly the medium, is the educational structure that provides this multidisciplinarity, which is absolutely necessary for these challenges. This is
We've found too, like a lot of students, especially if they're mechanical engineers or aerospace engineers, if they want to work in research, the natural inclination is like, well, I have to be in mechanical for research, but tell me if I'm right, the other disciplines like to have mechanical engineers in there because there's always something to build, right? There's always something that they'll need the strengths of a mechanical engineer. Is that true?
Absolutely, absolutely. There's no purely mechanical device. Take the paperclip. Take a paperclip maybe out of aluminum. To make aluminum, you need to convert an ore, it's called bauxite, into pure aluminum. To do that, you need to pass massive amounts of current in order to melt the aluminum, purify the aluminum, even trivial applications involve a multidisciplinary approach. The other point I want to make, and this reminds me, is that at the Hajim School, Dean Wendy Hazelman, our Dean of the School of Engineering of the Hajim School, has put together a very nice program. It's called the Grand Challenges Scholars Program, where a student at U of R can select one of these challenges and address this challenge from 5 different components. One is coursework, another one is international education, another one is research, another one is human needs, and there's a 5th item too. Therefore, you can actually pursue at U of R within the Hajim School one of these big challenges. I would like to tell students that I was born in the 20th century. You too, Nick, of course.
Yeah.
So the 20th century is where we became from children to adulthood. But for students entering the university, the 21st century, this is your century. This is their century. They will have to live with these challenges, no matter which country they actually live in. A little bit of information about our classes. You see here the class of 2023. You will see from here also basic structure of the freshman, the first year curriculum. The point I want to make from here is that the first semester is common to all engineering programs. Therefore, there's no need to declare one's major until after the end of the first semester. So let me talk here about let me shift here slightly into aerospace. I have here 4 examples that span aerospace and mechanical. Let's go very down to earth, so to speak. Designing energy efficient homes are clearly very important, so I don't waste energy, I don't waste power, and so on and so forth. Designing this effective, highly effective insulation is something that involves mechanical engineering, chemical engineering, and material science. On the bottom left, I have something that's one of the U of R highlights, and that is how to create clean, cheap, abundant energy in a process similar to how the sun creates this energy. It's called fusion. It's a highlight. There's probably 80 or 90 people at U of R working on this technology, on this science. Essentially, how to compress something that looks like a little spherical pellet, and this compression process liberate clean energy. So the cleanliness and the abundance of this energy is absolutely critical. Okay? Just to give an idea, the little sphere that you see there on the bottom left of the figure, this sphere is less than a speck of rice. It's about 1 millimeter in diameter. So think about think of a fourth of a grain of rice. That's how big this sphere actually is, and this can liberate a huge amount of energy. I have on the bottom right something that looks very esoteric and very complicated and colorful. It kind of looks attractive, but so essentially this is a model of fluid flow in the human brain as a way of understanding how blood flow in the brain may accelerate or decelerate degenerative brain-related diseases, illnesses such as Alzheimer's. And this is a collaborative project with the medical school. So all of a sudden we bring medical needs, and which human being does not have medical needs? No matter how young or old you are, everybody has it. And of course, right in the middle, I have the aircraft, and you can see from here that the aircraft has some fundamental components. And every time I see, when I'm out walking out, with my dog or like on a soccer field, and I see those aircrafts flying, I'm amazed at how effective, efficient, safe, and beyond belief flight actually is. Something heavier than air, significantly heavier than air, self-sustained flight with safety, with complete safety, and usually on time, right?
We get reminded of that being so close to the airport on
Yeah,
campus.
exactly,
You'll see
exactly.
a massive plane fly by, and they're like, "Oh my gosh, that actually it flies."
Yeah, we're about 6 miles from the Rochester airport. So on the U of R campus, you see aircraft flying over over the campus all the time. So we admire all the time. So let me talk here about something that is I did not quite mention explicitly, and that is engineering is a profession. I want to emphasize this. It's just like every profession, we have professional code of ethics. And I always, at this point, I will ask, if I give this a live presentation to students, I would like to ask them, does anybody here think of themselves as not being ethical? Of course, nobody. We all think of ourselves as being ethical. Every single person thinks, of course, I have my personal ethics. But the point I want to make is the distinction between professional ethics and personal ethics. In order to highlight this, I have from here a statement. It's the purpose statement. And I ask the students or parents or anybody else, is this true or false? Engineers, in the fulfillment of their professional duties, must carefully consider the safety, health, and welfare of the public. This sounds terrific. It's like a apple pie, motherhood. It sounds terrific. The statement is actually false. It is false because engineers do not carefully consider the safety. Safety must be paramount. And I always rephrase this to the students. If I have carefully considered the safety of my car, does this mean that my car is safe? Safety is the paramount factor in all engineering practice. So I cannot overemphasize this. Again, the way we approach aerospace design, of course, designs must be optimized. We need to quantify what we mean by optimized designs. And I have here some examples of light and stiff materials, such as aluminum, magnesium, and their compounds, and carbon fiber reinforced composites, which is the new technical material used for aerospace. But of course, one can also look about something economic and stiff. So if something that needs to be economic and stiff is the chair I'm sitting on right now has a steel sort of back, because it doesn't have to be particularly light, as long as it's stiff, so that my back, so I don't fall over, and it needs to be relatively cheap, so I can actually afford to actually buy it as a consumer. But there are other considerations which are becoming increasingly important in the 21st century. How do you design a structure that's environmental and stiff? How do we design a structure that's sustainable and stiff? And you see from here now we're looking at a little bit more vague concepts, the concept of what's environmental design, the concept of what is sustainable design. Therefore, we see from here that we can go from purely technical to more pressing aspects such as environmental, sustainable, which go beyond technical, right? What is environmental, what's sustainable is it's even a political issue. I mean, if you read the literature, the debates of the campaigns, you see that what is sustainable, what's environmental, what is economic. Clearly, this plays a very big role in our political life. Something that we emphasize in aerospace engineering is that every complex engineering structure, no matter how complex it is always analyzed in the 4 fundamental modes of deformation. That is tension, which may cause breaking, something that bends, something that is twisted or torqued, torsion, or something that's actually being compressed. And you can see from here that each of these materials has a different cross-section. But the point I want to emphasize is that these materials, these structures, are made not always from a solid material, but is made from a solid material, which may have a shape attached to it. So by optimizing the shape, I can optimize the performance of the material while minimizing its weight. So that's what aerospace engineering is all about. I will give from here an example of what the challenges that aerospace engineers have to face, both for commercial and defense-related aerospace. I have here an example of a gas turbine, which has a very high efficiency because it can operate at temperatures up to 1200 degrees Celsius. Okay, just to give an idea, a gas turbine is twice as efficient as a traditional fossil fuel power plant. Twice higher efficiency is a tremendous engineering accomplishment, but the temperature required on the order of 1200 degrees Celsius. And at that temperature, every known material that have easy access to is essentially a liquid or like a soft cheese. It becomes like almost the consistency of brie kind of cheese. Therefore, I cannot build structures with that. Therefore, the need for advanced materials that must withstand higher temperatures, a huge capability in aerospace engineering. And therefore, the idea of gas-related technology is important. So let's talk now a little bit about this. So now we talk here really the meat of aerospace engineering. On the top left, you will see I don't know if you can see my pointer. On the top left, this is the so-called Wright Flyer 1, December 17th, 1903, the first sustained heavier than air stable flight. The flight went for about for less than a mile, about 2/3 of a mile, and it took 1 minute. I always like to tell students that a mile is approximately the distance from CSB, the building we call Computer Science Building, to Fover Stadium. This about a mile or thereabout, and that flight took about 1 minute. I could probably jog that distance faster than 1 minute. Yeah. The point I'm making is that this technology demonstrates a fundamental idea, but clearly not optimized. And you'll see that here on the right-hand side, the Lockheed Martin stealth fighter, 100 years later, and you can see how much technology has actually changed. New materials, new propulsion, new designs, bizarre shapes, unlike anything the Wright brothers actually thought. I have shown on the bottom 3 space applications, which I think are very exciting. The Space Shuttle, the Voyager exploratory satellite, has been going on for, almost like 50 years. And the Skylab, which is also an Earth-related satellite for observing weather patterns, meteorology, and so on and so forth. Therefore, you see from here, aerospace. We use the term aeronautical when it comes to things that fly near the surface of the Earth. So aircraft is aeronautical. And things that need to go to space, from the Earth to space, we call this aerospace. So in 1903, when the Wright brothers demonstrated this significant achievement, it was all aeronautical. And now we have to be aeronautical and aerospace. Again, some examples to give you how much we've grown, so to speak. On the left-hand side is the Space Shuttle. The Space Shuttle has one main engine. The main engine is a supersonic nozzle. And you see that on the right-hand side, what the Space Shuttle main rocket engine looks like. Significantly larger in size than a human being. And you note from here, those circular, they almost look like ribs, circular ribs and axial ribs around the rocket engine. I won't say what the ribs are actually being used for, except to observe that this engine will withstand necessarily very high temperatures. So how do you prevent very high temperatures? You have to actively cool in order to prevent. Therefore, there are essentially active cooling mechanisms to make sure that the material from the Space Shuttle engine does not melt, essentially.
And I was at the Kennedy Space Center in Florida, and they're explaining how like a lot of the stuff on the outside in the picture on the left is steam, because they were melting the whole plant. Exactly. It's one of those things where I can imagine you're anticipating all these problems, but then you forget about what one simple heat problem can do to your launching space.
Yeah, and just to give you a more recent example, SpaceX, Elon Musk's, I think, very visionary company. One may like or dislike his political inclination, but that's a different story. But Elon Musk, SpaceX, the technology that makes SpaceX rockets viable and very impressive is that they have these active cooling mechanisms, which are very sophisticated. Okay, let me go back a little bit in history about aerospace engineering. Leonardo da Vinci, these days Leonardo da Vinci is everywhere. Leonardo da Vinci first proposed the notion of ornithopters, essentially flying devices that look like birds, flapping wings, just like birds. It turns out that Leonardo da Vinci, who was a brilliant man, was also self-educated. Therefore, a self-educated person could not tell if something that he proposed or thought about was very correct or very wrong. So it turns out that this notion of Leonardo da Vinci held back aeronautical engineering for about 300 years because he failed to identify the fact that to make something fly, you need a separate mechanism that creates lift than the mechanism that creates thrust. So that's why no aircraft are built in the shape of something with flapping wings. I need to separate the lift idea from the thrust idea. Very fundamental. 300 years later, George Cayley first demonstrates that what creates a lift must be a separate device from what creates thrust. And that's really the conceptual origin of aerospace. I would like to show from here some very impressive data. Actually, we discussed this data in this introduction to aerospace engineering course, literally as we speak. I have shown from here on the horizontal axis the development from 1903, the Wright brothers, to about 2010. And vertically is the flight velocity in miles per hour. Okay. The green horizontal line corresponds to the speed of sound at sea level. And you will notice from here that, for example, starting at about 1948 to be precise, the speed of sound barrier is broken by Chuck Yeager, as you may know, for the first time demonstrated scientifically and practically. But you will notice also that after that, a lot of the military technology, defense-related technology, doesn't necessarily try to attain very high velocities. As a matter of fact, we talk about the Mach number. I'll talk about this here in just a minute. If you look at the data on the right-hand side, MiG, a Russian aircraft, F-22, F-35, the Eurofighter 2000, you will see that these operate at about a Mach number 2, about twice as fast as the speed of sound, which begs a very interesting question. Why not try to go even faster for defense? So it's a very important capability, because it turns out that if you try to operate much faster than this, you sacrifice thrust, you sacrifice drag, and you sacrifice maneuverability. Therefore, you need to optimize a variety of different conditions in order to have a viable defense-related aircraft. One point that we try to convince the students that everything that flies is exposed to the exact same four forces, being lift, what creates lifting, drag, why you need thrust, what creates thrust, and of course the weight. Everybody is familiar with what the weight is. You step on a scale, 160 pounds, 180 pounds, and so on and so forth. But the point from here is that you see from here in the middle, the hummingbird, on the right-hand side, a seagull, on the left-hand side bottom, the Airbus A380, which is massive, and on the right-hand side bottom is the Boeing 747. These are really gigantic aircraft. And the thing that to observe from here is that all of these flying structures obey the same scientific principles, which means you have to govern the lift force, the drag force, the thrust force in relation to your weight. Again, I talked about a little bit about control devices. Here very briefly, I have shown from here in an aircraft the flaps, the ailerons, the elevators, and the rudder, which are used to control flight. And again, the point I want to emphasize that if you're walking on a floor, or if you drive a car, it's very easy to make a turn, because the contact with the road will ensure that you can actually make the turn, or I can stop immediately on my tracks if I'm walking on Earth. But an aircraft cannot do that. So an aircraft needs these additional geometrical structures to ensure that flight can be accelerated, slowed down, and so on and so forth. Something that, again, this material, we talk about in the Introduction to Aerospace Engineering course. The figure on the bottom right is something from the second lab that the students actually do. I have a picture of an airfoil. You see from here how air flows from the left to the right in that airfoil. The airfoil doesn't care about the air. The airfoil cares about the fact that there are pressure forces and there are shear forces acting on the airfoil. The pressure forces, if designed correctly, will generate lift. The shear forces will create the drag. So you need the thrust to overcome the drag. That's the point on the left, the big graph. This is called the Great Flight Diagram. It's one of the most impressive things that we actually discussed in the first semester Introduction to Aerospace Engineering course. Essentially, this covers anything that flies. The bottom orange oval corresponds to the fruit fly. The top orange corresponds to the Boeing 747. And based on what we learned in our first class, we can compute literally within 3 weeks of this class, the straight line that goes from the bottom that goes from the southwest to the northeast. Notice from here that the closer I go to modern technology, the closer I move to the top right, the closer the correlations between what a first-year student can do in aerospace engineering and the actual technology. The Fokker, the Boeings, the Airbuses, and of course the flying jets here as well. This is awfully impressive that a high school kid within 4 weeks of entering the university in aerospace engineering can actually understand these basic forces.
Yeah, I mean, it gives it so much context that they will already be sort of somewhat exposed to, and then can really visualize like the. Of
course, I don't think there's a single person who hasn't been very bothered by having fruit flies. You know, you leave a peach or an apple on the counter for like a couple of hours, you start getting so fruit flies, you can hardly see them. Fruit fly, the same principles as the Boeing 747. Oops.
Amazing.
Oops. Yeah. What happened here?
There we go.
There we go. Let's talk a little bit about the science that everybody will understand. Aerospace engineering has two what we call significant, hugely significant, critically important numbers. One is the Mach number, which tells you how much faster you move from the speed of sound. And the critical value for the Mach number is 0, something standing still, 0.3, kind of a two-seater airplane that you see people fly, you know, on a nice sunny Saturday morning. Mach number 1, breaking the sound barrier, and Mach number 5 and above, which is what we call hypersonic. So this creates what we call incompressible subsonic, compressible subsonic, supersonic, and hypersonic. So these ideas are discussed in a technical context in aerospace engineering. The second one is the notion of the Reynolds number, which distinguishes what we call laminar versus turbulent flows. Very important. Laminar flows are wonderful because they minimize drag, but turbulent flows is a reality of life. So the idea is you want to mimic what you like, having to live with turbulence. Understanding turbulence is a huge technical problem. What distinguishes blunt versus streamlined or slender kind of geometries, whether flow is attached or flow is separated. Flow separation leads to what we call stalling. Stalling is very bad because when something stalls, it loses lift. So you kind of fall, really free fall through the air. And lastly, what's the effect of smoothness or roughness of a wing or an aircraft body in this correlation? Let me talk here about propulsion because this is very exciting. The standard propulsion sort of technology is what's called the propeller. The geometry of the propeller is essentially an airfoil, is essentially a wing. So a propeller creates thrust in the direction in which the lift force is actually being created. This is the old technology, and it involves essentially the reciprocating engine. The reciprocating engine first happened about 140 years ago. Okay? The company that eventually became Mercedes-Benz, named after the daughter of Benz. The daughter's name was Mercedes. First patented and used extensively the internal combustion engine. This technology is 140 years earlier. On the bottom left, I have a little gadget that has been demonstrated that the ancient Greeks actually invented, which demonstrates how by using steam, one can create motion. But of course, this did not produce the steam engine because it was more like a gadget, like a curiosity. One would show to your wealthy friends over dinner time and saying, oh, look at this cute gadget that somebody actually gave me. Perhaps the most important part for modern technology is the turbojet, the jet engine, which essentially uses combustion of a gas in order to create very high exit speeds, which therefore create a thrust in the forward direction. This is an example, what you call the fan jet, because it has both a fan up front, and then you'll see that it has a compressor and a turbine. So the question becomes, why do you need a compressor and why do you need a turbine? And the answer is that adiabatic compression. A compressor is used so that when you compress something very rapidly, its temperature goes through the roof. Therefore, you can ignite it very easily. So you need the turbine to drive the compressor, to create combustion, to create the flow exiting the jet engine. So the technology, the point again I'm making from here is that each of these components is a separate component But the system is a collection of these components. And again, going back to what mechanical and actually all engineers, aerospace engineers actually do. Assess, analyze, break. No, first assess the problem, analyze each component separately, and then design this. This is a different kind of technology. You'll see that on the top right, this is a turbofan. So these gigantic jets like the Boeing 747 and the Airbus 380 are all driven by turbofans. On the other hand, turboprops are used for smaller, let's say for executive style type of jets, like Lear jets and so on and so forth, which begs the question, why are big flying objects use a turbofan and smaller flying objects use a turboprop? It turns out that both the turbofan and the turboprop are not good enough for defense applications because you need to go significantly faster. So now we're looking about the Ramjet and its more recent incarnation, which is called the scramjet. So essentially what the Ramjet is, it's exactly this. You have that ram on the very front, and if this ram moves through air very rapidly, it compresses air because it simply rams into the air. Therefore, compression takes place automatically for free, if you like. Oh. The only problem with this technology is that to get this to happen, you must already be moving at a very high speed. So the question, how do you move at a very high speed? Somebody has to lift this device up on the air, give it a high enough speed, and then it becomes self-propelling. Oh my gosh. Therefore, you see from here how the different components create different issues. Each is solved all together, and then we put the full system actually here together. Let me talk a little bit about here wind tunnel testing. First, you will see that on the top, this is the NASA Ames Research Center. You can see from here the size of the cars. This is a very big wind tunnel, which essentially NASA uses to test airfoils, and a lot of this information is actually passed on to the wider aerospace community. So this is the example of what we call a subsonic wind tunnel. On the middle, we have a supersonic wind tunnel. And on the bottom, we have the exact same idea. This is called the rocket engine nozzle. And you will see that the supersonic wind tunnel and the rocket engine nozzle, they have a lot of similarities and a lot of differences. And you will see that on the right-hand side, you will see what a rocket engine nozzle actually looks like in relation to a human being. And you will see that this geometry next to the human being looks identical to the geometry of the rocket engine nozzle on the left-hand side. As a matter of fact, this problem of the rocket engine nozzle was on the first midterm exam that the students took in Introduction to Aerospace 2 weeks ago. The students did very well. The average was about 90, so everybody did very well at that. But
that's good.
My point is that we analyze problems which are relevant to aerospace with very, I don't want to say minimal, very, very small amount, but very guided amount of information in aerospace. Instead of saying, oh, I'm going to read everything I can on Google or Wikipedia about aerospace engineering. The last slide I want to talk is about space propulsion rockets. The person, you will see that on the top left, this is Robert Goddard. The NASA Goddard Space Center in Maryland is named after him. He was very unfortunate because he was the father of rocketry. Okay? But he died before rocketry actually became a reality. So he died very unhappy, very unrecognized, and essentially very lonely, which goes to show that technology sometimes is so advanced that the rest of the world does not appreciate how breakthrough that technology actually is. For the case of the space shuttle, for the case of rockets, the rockets must carry their own fuel and oxidizer. For earthbound applications, air is the oxidizing medium. It has a lot of oxygen in it. About 0.25% of air a quarter fraction of air is oxygen. But in space, there's no air, there's no oxygen. Therefore, I must carry separately the fuel and the oxidizer. And the technology for how do you carry these two separate and how you'll make sure that they don't mix before the intended mix-up process is absolutely fascinating. Huge technology by NASA in there. Now, it turns out that when you look at really outer space, there's nothing to retard motion, Therefore, you simply need a little bit of a push, and this little bit of a push will take you very, very far. So an example of this, the electric ion thruster, which involves, of course, an electric technology, which essentially ejects ions at a very slow rate. And as a result, motion takes place in the opposite direction, just like a rocket, but there's absolutely no resistance. There's no medium to be overcome during this motion. The last slide I want to present is that clearly aerospace, there are a lot of defense-related applications in aerospace, right? Right now, there's a war going on between Ukraine and Russia. There's a lot of military action in Israel, Gaza, and in Lebanon. There's a lot of military action in Yemen. The world is afire, so to speak. The point I want to make is that a lot of this military technology, by necessity, is related to aerospace. On the other hand, my personal belief is that some of the hugest contributions to humanity is done also through aerospace. I have here on the left-hand side the International Space Station, which is actually it's in action right now. The commander of the International Space Station right now, Commander Williams, is a woman with a degree, as you can imagine, in aerospace engineering. And the nice thing with this is that this is a very multinational collaboration. USA, Canada, Europe, Russia, and Japan. And you may want to ask yourself the question, where else have all these 5 entities collaborated? Can you identify one example where they have all collaborated? Maybe in the Olympics, yeah. But as we know by now, in the Olympics, Russia did not take part in the most recent Olympics. They did not take part in the most recent World Cup. Therefore, but in the exploration of space for humanity, massive collaboration. The other point I want to talk about is Apollo 1969. I have this picture on the bottom right that Armstrong is shown there with the American flag. You know, one can feel very nationalistic about this, great accomplishment, but you need to recall what Armstrong said when he landed on the surface of the moon. You know, one small step for a man, a huge leap for mankind. Let's talk about a huge leap for humanity. Therefore, although Armstrong planted the American flag on the surface of the moon, he was thinking about the contribution to humanity that this new adventure, which succeeded, which successfully was concluded, and of course everybody got back on Earth, actually demonstrated. So my point of view is that that technology may be used for defense-related purposes, but technology also unites. Therefore, I want to convey this message because in a university, we want to be able to do the technical and scientific training of our students that can be applied to solving human needs. So I would like to remind you again, the greatest challenges for the 21st century, those 14 multidisciplinary, vague challenges, and how technology and science and engineering is used from a first-year student to a mature graduate student, to faculty members, to very recognized scientists to solve these problems. So that's the end of my presentation, Nick. I hope this was entertaining. I always like to think that whenever I talk, I entertain people, but
and I like the idea that it's a complex and positive message going forward. I mean, the idea of aerospace literally elevating all of these discoveries that we now, with the development of this, we can now say things that we never thought were possible now seem theoretically possible, and then
absolutely
a little bit more practically possible. I wanted to ask you a little bit about the assess, analyze, design in terms of what does it look like in terms of time spent for each, and who is this done with? So if when you're in each section, you know, how does that look like for a young scientist or somebody who's interested in those 3 parts?
So let me go to the very beginning. Yeah. So I will tell you, in the past 35 years, I have consulted for upwards of 40, 45 companies, small companies, large companies, over 35 years. When a problem is actually described by a corporation or a small company, big company, doesn't matter. They know there is a problem, but they cannot even describe what the problem is in a technical context. If they say, well, change this material from aluminum to steel, then they don't need somebody with knowledge to actually do that. But they say, well, I have this material, and this material seems to fail about 10% of the time. I cannot afford to have a 10% failure rate because my customers are not happy about this. What's going on? So they don't even know. So assessing means that you need to provide a quantitative context for identifying the problem. It's not sufficient to say, well, let's get if I'm if I'm Wilbur Wright, I need to design the Wright Flyer 1 to take me from the Earth, to fly at the height of, for a distance of less than a mile. I need to take this problem, break it down into individual components, assess the difficulty, complexity, or perhaps ease of each component separately, and then put this together. I will tell you that the Wright brothers did a huge amount of technical work before the Wright Flyer 1. And when I say technical, I mean real engineering. They designed their own propulsion, their own engine. They designed, optimized their own wings. They optimized the length of the wings and the shape of the wings. And for this, they had to do extensive assessment. They analyze the problem, and finally they design and build what. So the result of the design is what you actually see and what really impresses people. So in the context of a technical problem, the assessment would be probably 20%. Okay? The analysis will be approximately 30%. And the design, and of course the subsequent part of design is design and manufacture. So the design would take another 50%. So between assessment 20%, analysis about 30%, the design about 50%. And I did not talk about this, but roughly the undergraduate curricula in the different engineering programs at U of R, very roughly speaking, have this assessment description about 20%, analysis about 30%, and a lot of emphasis on design, especially through the 4 years, but very heavily in the third and fourth years. So 20, 30, 50% altogether.
That makes sense. I was thinking about, when you're presenting, I'm thinking about Goddard and the Wright brothers and their introduction into trying to discover what is possible. With students today, this is the point where they're going to start to learn some of these concepts and really understand what is possible. But I want you to go back to when you were, about 18. And I want you to think about what your impressions or interests were in aerospace in that time, and how did you get to where you are now, or how did aerospace get there from here?
Yeah. So I grew up in Greece, in the country of Greece, and when I was 18 years old, I was given a scholarship to do some sports, to play sports, and to also study at Brown University. So I flew to the United States. Still remember, with the TWA. TWA doesn't exist anymore as a company, right? With the Boeing 707. As an 18-year-old, I started majoring in chemistry because I loved chemistry in high school. From chemistry, I shifted to chemical engineering. Too much chemistry. I still love chemistry, by the way, but too much. And then I shifted to mechanical engineering. Now, the aerospace I was exposed to when I was 18 years old was very, very consumer based. In other words, you board an aircraft, you don't think, will I end up safely or not when I fly from Athens to Boston Logan Airport? You take it for granted. And I think that most people take this for granted. They better take it for granted. Air transportation has to be extremely safe. But of course, for these projects that NASA is working on, for these breakthrough projects, single prototypes, safety is very important, but it cannot be assured with complete certainty. You see you need the Space Challenger accident. You see failed rockets. You see failed rockets by all kinds of national kind of efforts. So the state of the art of aerospace, there are a lot of risks, but of course there are also a lot of rewards. But the point, the answer to your question is, when I was 18 years old, I was a consumer of air transportation. I was taking safety and convenience and speed for granted because I didn't know any better.
Now, what do you think the biggest misconception is about the aerospace engineering field now, and what can we do to counter that?
I think that I will tell you that I see the contact between mechanical and aerospace as being, I would say, roughly 75% overlap, and as I said at the beginning, about 25% different to mechanical and aerospace. One big misconception, especially among younger students about aerospace, is that a person will design something that looks like a SpaceX rocket that will take you to from the surface of the Earth with this spectacular take you out to outer space and then return exactly in the landing base with it takes a huge amount of effort. I would say that in SpaceX there must have been easily 300 people, if not more, that worked on this project. And each person, each aerospace engineer or mechanical engineer or chemical or electronics or computer science person, a lot of coding, of course, is required for the control systems. Each executes a small fraction. So I think that a misconception is that I'm not Orville or Wilbur Wright. The two of them started everything from scratch, built everything from scratch, and demonstrated it. But that was in 1903. Now we're 121 years later. Each engineer will execute a certain function, and then the teams will get together. They will brainstorm. They will exchange ideas. They will communicate. They will communicate with their management in order to move forward by building the bigger system. So it's a misconception to think that the person can design to build, for example, a car. To build a new car, take this. What's a small car? Let's take a Honda Civic, a small car. When we're looking at trucks or racing cars, to build something like a Honda Civic, there must be easily up to several thousand people who've been involved with the design and manufacturing of a single car. And car is a very consumer kind of convenience, right? Everybody's driving something safe and mileage and so on and so forth. So in engineering, engineers work in teams. Each team is executing a small part of the bigger design. And then more teams have to communicate to ensure that combining the different components into a bigger system is done safely and seamlessly.
So what do you think then is the next big wave, or the next thing that we haven't really scratched the surface of, or we might have just scratched the surface of, that we're on the lookout for people who are going to be joining the field in the next 20 years?
Yeah. So I will tell you that whether you agree with this idea or not, aerospace, there's a significant defense-related component. And you say, oh, defense-related, that sounds good. Everybody wants to be defended. But another way of saying defense-related means it's technology you use to kill other people, basically your adversary. That's what it is, the fact of life, right? It's humanity we have been killing each other, for thousands of years. Mm-hmm. But the point I want to make is that in the area of, let's say, broader human-based technology, I see huge benefits in the area of space exploration. The Earth is getting crowded. We may have to deal with the global warming. You may disagree with who is responsible for global warming. If you're a Republican, you say something. If you're a Democrat, you say something different. If you're a scientist, you say something different yet, but that's a different story. But the point is that access to space is becoming almost a commodity. People will now actually pay, billionaires to actually travel with SpaceX. Other countries than the United States have attempted to and will be soon attempting to make landings on the moon, exploration of other planets for raw materials and so on and so forth. So the two applications I see furthering of defense-related applications. Let's kill each other effortlessly, and that involves the idea of hypersonic missiles, hypersonic aircraft, and so on and so forth. And the other big technology is the space part of aerospace, the space exploration safely at the human level, not at the defense or military related kind of level.
Makes sense. So I have one more question for you, and I know that you advise a lot of students, especially the ones who are in their first year. I want you to go to a little bit younger audience. So I want you to think about what type of advice would you give someone in high school that's interested in aerospace after they watch this video? What's the next thing that they should do if they're interested in aerospace engineering?
I think to do something to do would be to determine, in my opinion, between a career in mechanical engineering versus a career in aerospace engineering. Let me tell you what I mean by this. Mechanical engineering has been around for a very long time. And mechanical engineering, no matter how well or how poorly the national economy or international economy does, mechanical engineering and mechanical engineering are always in demand, steady demand. You'll never be out of a job if you're a mechanical engineer. In aerospace, the aerospace industry has cyclical ups and downs that kind of match. Maybe there's a little bit of lag behind the national or international economy. I mean, you know, right now that Boeing, for a variety of obvious reasons that we've been reading about in CNN and BBC and NBC, clearly Boeing has some significant technical problems to overcome and some significant public relations problems to overcome. So my point is that aerospace is more cyclical. So the advice that I would give to students is, do you want to put your education into a field such as mechanical engineering that will be steady for the next 30, 40 years? And then add something like a minor in aerospace. So you can work in aerospace, but if aerospace goes south or partially south, you always have the mechanical engineering portion. Or would you rather put all your eggs into the aerospace engineering and saying, I would rather major in aerospace engineering because this is what I love? And I think that both approaches are very valid. There's no right or wrong approach. If you say, I'm crazy about aerospace, that's the only thing I want to do, then you should go out towards a major in aerospace engineering or a master's degree in aerospace engineering, something along those lines. But in terms of career advice that I give to an 18-year-old is think what you will be doing 30 or 40 years after you graduate. Let's assume that that things proceed without unforeseen health or financial or familial or political. Let's say that things proceed according to plan. What's your plan? How will you function when you're 40 years old? Oh, you're 50 years old. When you're 60 years old, because education only. So I think that sort of balancing this need for long-term stability versus shorter-term intellectual interests is something that each student must balance on their own, maybe in discussion with their parents, maybe in discussion with their counselors, although I think that high school counselors are very typically, they're very ignorant of what engineering is. So they need people like you and I and faculty members and advisors to be a little bit broader educators of what is engineering. How do you describe engineering, whatever engineering may be, to a 17-year-old? If they have no parents or relatives who are actually engineers that can actually bounce ideas from. So I think that we have to do a much broader campaign to educate the wider 15 to 70-year-old population nationally as to the opportunities that engineering provides. In my concluding slide, I mentioned that aerospace really solves human level problems, and Armstrong identifying a huge leap for mankind. Clearly, he wasn't saying a huge leap for America. Right. He said a huge leap for mankind. Therefore, I think this addresses the fundamental need of the human being to move through air. Is something, it's built in our DNA. And there are many different ways to actually do that.
I love it. No, that sounds great. It does make sense because the students, I felt in the last 10 years, have been more global, right? They've understood and thought more in this level. And something like aerospace is that opportunity, right? Like you're saying, if we can continue these types of collaboration.
Yeah.
So, Dr. Lambropoulos, thank you for your insight and spending this time with us. I mean, it really does help, especially to be able to for students who don't have a technical background and get this really good overview and understand it. And then also know that they have choices between mechanical and aero at the university as well. So,
yeah. Nick, before we hang up, if you want to put my email address, which you have in the video, maybe in some kind of remaining slide, something or other. Absolutely. If any students or parents want to contact me about more details, I'll be more than happy to talk to them.
Absolutely. No, we will do. That sounds great. The full spectrum series has explored other areas such as biomedical, chemical, and audio and music engineering, and much more. You could check these videos out on Facebook or YouTube page. On behalf of the Hajim School, thank you for watching, and we hope to see you soon.